Tonight on ZZZcience, we'll drift together into the quiet corners of the universe. Whether your mind is racing or your body just needs rest, these gentle stories of science are here to help you slow down and drift off with ease. For all the discoveries we have made, the universe is still filled with puzzles, paradoxes, and quiet mysteries that no one can fully explain. Some are cosmic, stretching across galaxies and black holes. Others live here on Earth, in the oceans, the atmosphere, and even in our own bodies. These unanswered questions remind us that science is not a book of final truths, but an endless story still being written. Each mystery holds a doorway to wonder, a reminder that we are explorers in a universe far bigger than we can yet comprehend. If you enjoy drifting off to scientific wonders, feel free to like and subscribe, or simply share your thoughts down in the comments. It helps others find their way here, too. But for now, let these questions carry you. And if you are ready, let us begin. We still do not know why the universe exists at all. It seems like the most basic question imaginable. Why is there something instead of nothing? And yet, science has no answer. Physics can describe how the universe behaves once it exists. Cosmology can trace events back to the Big Bang. But why there is a universe at all, why there are laws that allow it to exist, remains unsolved. Quantum physics suggests that what we call nothing is not truly empty. Even the vacuum of space teems with activity, fleeting particles that flicker into being before vanishing again. Some physicists suggest that the universe itself may have arisen in the same way, that absolute nothingness is unstable and something must always emerge. Others argue that perhaps our universe is only one of countless universes in a vast multiverse, each popping into being with its own laws. But if that is true, we are only pushed back to a deeper question. Why should the multiverse itself exist? Philosophers sometimes propose that existence is simply the natural state, that non-existence is impossible. Perhaps reality in some form must always be. But these are ideas we cannot test. No telescope, no particle collider can measure why there is being instead of nothing. Every other question in science rests upon this one. Every star in the sky, every atom in your body, every law of nature, all exist on a foundation we cannot explain. The fact that reality is here at all remains the deepest mystery. We face the spark that set the cosmos in motion remains a mystery. We can trace the universe's story back nearly 14 billion years, to an age when it was a hot, dense fireball. We call this beginning the Big Bang. But what actually caused it? That remains unknown. Cosmologists have pieced together a detailed history from the moment the universe was only fractions of a second old. In that first instant, rapid expansion, called inflation, may have blown space itself wide open. But what triggered inflation? Why did it start? And why did it end? These questions remain unanswered. Some theories imagine the Big Bang as a quantum fluctuation, a tremor in the fabric of reality that gave rise to space and time themselves. Others suggest that the Big Bang was not the first event, but only one moment in a cycle of births and deaths, with universes expanding, collapsing, and beginning again. What complicates the question further is time itself. If the universe includes the birth of time, then asking what came before may not even make sense. Our instruments, the Hubble Space Telescope, the Planck satellite, and the new James Webb, give us snapshots of the infant universe. But none can peer into the first instant itself. We know the universe began. We can measure its age, chart its growth, and study its afterglow. But the spark that set the cosmos in motion, the true first cause, is a mystery still hidden in the dark. Time always flows forward, but no one can explain why. Every moment, the present slips into the past. We remember yesterday, but not tomorrow. A broken glass never leaps back together. Heat moves from hot coffee into the air, but never the reverse. Time, in our experience, only flows one way. This is called the arrow of time. What makes it strange is that the fundamental laws of physics do not require this. At the smallest scales, particles can move forward or backward in time with equal consistency. The equations are symmetrical. Nothing in them demands that time should only advance. And yet, our entire world depends on this one-way street. Scientists often connect the arrow of time to entropy, the tendency for disorder to increase. The universe began in an exceptionally ordered state and has been running down ever since. But why did it begin that way? Why should the cosmos have started in such a low entropy condition that time could even have a direction? Some physicists think the arrow of time might emerge from the way information spreads. Others suggest it is tied to the expansion of the universe itself. But none of these explanations are complete. Time's direction is something we live inside of every second of our lives. And yet, why it flows forward, and only forward, remains one of the most haunting mysteries of science. Most of the universe is made of something we cannot see. When astronomers measure the way galaxies spin, they find something strange. Stars near the edges move far too quickly, as if held by an invisible force. By all logic, those stars should drift away into space. Instead, they remain bound. The conclusion is inescapable. Most of the mass in the universe is not visible to us. We call it dark matter. Dark matter neither glows nor absorbs light. Telescopes cannot see it directly, yet we know it must be there, because its gravity shapes everything around it. It holds galaxies together, bends the paths of starlight from distant clusters, and leaves faint ripples in the pattern of the cosmic web. So, what is it? Scientists have searched for decades. Some think it is made of undiscovered particles, perhaps WIMPs, or weakly interacting massive particles. Others suggest exions, ghostly particles that barely interact with ordinary matter. There are even theories that dark matter could be black holes formed in the earliest moments after the Big Bang. Despite enormous effort, we still do not know. Experiments buried deep underground wait for a passing dark matter particle to collide with a single atom. So far, none have. For now, this hidden mass, 5 times more abundant than ordinary matter, remains one of the universe's greatest unsolved mysteries. An invisible force is stretching space apart faster and faster. In the 1990s, astronomers studying distant supernova expected to see the universe's expansion slowing down. After all, gravity should be pulling galaxies back together. Instead, they discovered the opposite. The universe is not just expanding, it is accelerating. This means some unknown energy is embedded in space itself, pushing galaxies away from each other at ever-increasing speeds. We call it dark energy, though the name is only a placeholder for our ignorance. Dark energy makes up nearly 70% of the entire cosmos, yet we do not know what it is. One idea is that it is a property of the vacuum, a kind of constant energy present in empty space. Another possibility is that it points to new physics, perhaps a dynamic field that changes over time. Some theories even suggest it could be a sign that our understanding of gravity itself is incomplete. What makes the mystery even more unsettling is its consequence. The universe's fate depends on this invisible force. If dark energy remains constant, galaxies will drift farther apart until only empty space is left. If it grows stronger, it could eventually tear apart galaxies, stars, and even atoms. We can measure its effects, but we cannot see its true nature. Dark energy is the unseen hand shaping the ultimate future of the universe. The laws of physics seem tuned for life in ways we do not understand. The universe appears balanced on the knife's edge. If gravity was slightly stronger, stars would collapse too quickly. If it were weaker, galaxies might never form. If the electromagnetic force were different by a fraction, atoms would not bind together. Even the tiniest changes in the constants of physics could erase the possibility of life altogether. This puzzle is known as the fine-tuning problem. Why should the laws of nature have exactly the values they do? There is no obvious reason for gravity, electromagnetism, or nuclear forces to take the strengths they have. And yet, if they were different by even a little, our universe would be lifeless. Some argue this is coincidence. Others suggest that countless universes exist, each with different laws, and we simply live in the rare one where life is possible, a cosmic lottery win. Another idea is that there may be a deeper principle, still undiscovered, that forces the laws to take these exact values. For now, we cannot say. But when we look around at stars, planets, and the fact that we can even ask this question, we are reminded that the universe feels improbably, uncannily suited for life. And why that is so remains one of science's greatest mysteries. No one knows if the universe goes on forever or ends somewhere. The observable universe is vast, about 90 billion light-years across, but we cannot see beyond it. Light has only had so much time to travel since the Big Bang, and so there is a horizon we cannot look past. But what lies beyond that edge? One possibility is that the universe is infinite, stretching endlessly in all directions with no boundary at all. If so, then space may contain an unending number of galaxies, stars, and perhaps even other Earth-like worlds. Another possibility is that the universe is finite but unbounded, like the surface of a sphere. In such a universe, if you could travel far enough in one direction, you might eventually return to your starting point. Scientists search for answers in the cosmic microwave background, the faint afterglow of the Big Bang. Its patterns might reveal the universe's shape. So far, the evidence suggests that the universe is very nearly flat, but this does not settle the question of whether it is infinite. For now, we do not know if the cosmos stretches without end, or if it loops back on itself. The true size and shape of the universe remain hidden, just beyond our reach. Beyond the horizon of what we can see, there may be endless unknowns. When we look into space, we are also looking into the past. The most distant galaxies we can see are sending us light that has traveled for over 13 billion years. But beyond that lies a region forever hidden, the unobservable universe. This cosmic horizon is not like a physical wall. It is a limit set by the age of the universe and the speed of light. Beyond it, reality continues. But we can never know exactly what is there. Perhaps it is much the same: galaxies, stars, and planets stretching far beyond our sight. Or perhaps it is radically different, with regions governed by different conditions or even different physical laws. Some theories of inflation, the rapid expansion thought to have occurred right after the Big Bang, suggest that our observable patch is just one bubble in a much larger reality. If true, the vast majority of the universe lies forever beyond what we can measure. We are bound within a cosmic island. The sky we see is only the smallest fraction of what may exist. The rest of the universe is out there, silent and unreachable, a permanent unknown. Some scientists believe there are other universes, but we cannot prove it. The idea of the multiverse is one of the boldest in modern science. It suggests that our universe may not be unique, but one of countless others. Each universe could have different laws of physics, different histories, even different numbers of dimensions. The concept arises naturally in some theories. Inflation may create bubble universes, each budding off with its own conditions. String theory predicts a vast landscape of possible realities. In such scenarios, our universe is simply one outcome among many. This could even explain we live in a universe suited for life because only in such universes can observers exist. But there is a problem. If other universes exist beyond our cosmic horizon, we may never be able to observe them. No light or signal could ever cross the boundary. This makes the multiverse both fascinating and controversial. It stretches the definition of science, because an idea we cannot test may never be more than speculation. Still, the possibility that reality is larger than our universe, perhaps infinitely larger, is one of the most intriguing mysteries in physics. Space and time may be woven from deeper rules we have not discovered. Einstein's general relativity shows us that space and time are not fixed backdrops, but flexible and dynamic. They bend, curve, and stretch, shaping the paths of planets and the flow of light. But what, at the deepest level, is this fabric made of? At the smallest scales, relativity and quantum mechanics clash. Space and time seem smooth in relativity, but quantum theory suggests that everything should be grainy, fluctuating, and uncertain. Reconciling these two views is one of the greatest challenges in science. Some ideas suggest that space and time are not fundamental at all. Instead, they may emerge from something deeper, perhaps a network of quantum information or entanglement patterns that give rise to geometry. In this picture, what we call space-time is like a surface, and underneath lies a more basic reality we cannot yet see. Others wonder if time itself is even real, or if it is an illusion created by deeper processes. If so, our most basic intuition about reality would be wrong. Space and time feel like the stage on which the universe unfolds, yet the stage itself may not be what it seems. What they truly are remains one of the most profound unanswered questions in science. A single particle can be in two places at once, and we do not know how. Quantum mechanics tells us that particles do not have definite positions until we measure them. Instead, they exist in a superposition, a kind of probability cloud where many outcomes are possible at once. An electron can be here and there, passing through both slits of an experiment simultaneously, interfering with itself like a wave. Only when we look does the particle choose a place. This is not just theory. Experiments have shown superposition at work, not only with electrons, but with molecules thousands of times larger. Physicists can even create delicate states where objects exist in overlapping possibilities. And yet, no one truly understands what it means. Does the particle physically exist in two places? Or is superposition just a reflection of our incomplete knowledge? Some interpretations suggest multiple realities split, one where the particle lands here, another where it lands there. Others suggest reality itself is fuzzy until it is measured. Whatever the case, the ability of a single particle to seemingly be in two places at once remains one of the strangest, most unsettling mysteries of modern science. Asterisk. Entangled particles echo each other across light years, defying explanation. When two particles become entangled, their properties link in a way that ignores distance. Measure one and you instantly know the state of the other, no matter how far apart they are. Einstein called this spooky action at a distance because it seemed to violate the cosmic speed limit. Nothing should move faster than light. Yet experiments confirm entanglement is real. Photons, electrons, even small groups of atoms have been entangled and separated by kilometers. No signal appears to pass between them, but the correlations remain perfect. It is as though nature itself keeps a hidden ledger, ensuring that the outcomes stay in sync. What does this mean? Some physicists suggest reality is not local, that the universe is woven together more deeply than space and time allow us to imagine. Others think entanglement may point to hidden variables we have not yet discovered. Still others propose that information itself may be the foundation of reality. We use entanglement in quantum computing and secure communication, yet we cannot say why it works. The universe whispers across distance, and we still do not know how. No one knows why observing something seems to change what it is. One of the strangest discoveries in physics is that the act of measurement affects the system being measured. In the famous double-slit experiment, particles behave like waves when no one is looking, creating interference patterns on the screen. But if we measure which slit a particle goes through, the wave-like behavior vanishes. The outcome changes simply because we observed it. Why should this be? One explanation is that the wave function, the mathematical description of all possible states, collapses into a definite outcome when observed. But what counts as an observer? Is it a measuring device, a human consciousness? Or is collapse just an illusion, hiding deeper laws we do not yet see? Some interpretations say every possibility happens, branching into multiple universes. Others suggest that particles only appear definite when information about them becomes irreversible. None of these ideas have been proven. What we do know is that the line between observer and observed is not as simple as we once believed. The universe seems to care whether it is being watched, and no one knows why. Gravity is far weaker than every other force, and we do not know why. Gravity rules the cosmos. It holds planets in orbit, shapes galaxies, and governs the motion of stars. And yet, compared to the other forces of nature, it is unbelievably weak. A small magnet on your refrigerator can easily overcome the pull of the entire Earth. Why is this? The electromagnetic force, the strong nuclear force, and the weak nuclear force all operate on tiny scales with enormous power. Gravity, by comparison, is feeble. Physicists have tried to explain this hierarchy problem for decades. One possibility is that gravity spreads into hidden dimensions we cannot see, diluting its strength. Another is that the true scale of gravity is strong, but it is masked by unknown physics at small distances. Despite centuries of study, we still do not understand why gravity is so much weaker than the other forces. This imbalance is not just a curiosity, it is fundamental to the structure of the universe. Without it, stars and galaxies could not exist. The weakness of gravity is the quiet mystery that makes the cosmos possible. Einstein's universe and the quantum world both work, yet they refuse to fit together. General relativity describes the large-scale universe with unmatched precision. Quantum mechanics explains the microscopic world with astonishing accuracy. Each theory has been tested to extremes, and both pass every experiment we can throw at them. but they do not agree with each other. When we try to describe situations where both matter and gravity are quantum, like inside black holes or in the first moments of the universe, the equations break down. Infinity piles upon infinity. The two frameworks are mathematically incompatible. Physicists have searched for decades for a theory of everything that unites them. Candidates like string theory and loop quantum gravity offered tantalizing possibilities, but no experiment has confirmed them. Without a unifying theory, we cannot truly understand the birth of the cosmos or the nature of space-time at the smallest scales. The fact that our two most successful theories describe different realities is one of the greatest paradoxes in science. Both work perfectly, and yet together they fail. The true heart of a black hole remains unknowable. Black holes are regions where gravity is so strong that nothing, not even light, can escape. As matter falls inward, it is crushed toward the center. According to Einstein's equations, everything collapses into a single point of infinite density, a singularity. But infinity is usually a sign that our math has failed. What truly lies at the heart of a black hole? Some think the singularity is real, a place where the known laws of physics break down. Others believe a deeper theory, perhaps quantum gravity, will replace the singularity with something else, a loop of space-time, a finite core, or an entirely new kind of object we cannot see inside. The event horizon hides the interior completely from view. For now, the heart of a black hole is sealed away beyond observation and beyond certainty. It remains one of the most inaccessible mysteries in all of science. We still do not understand what singularities really are. A singularity is a place where our equations predict infinities, density without limit, curvature without bound, time and space collapsing into something beyond definition. Black holes contain them. The Big Bang may have begun with one, but what are they really? Are singularities actual features of nature, or are they signs that our theories are incomplete? Many physicists believe they point to the limits of Einstein's relativity. Somewhere beyond, a new theory, one that merges relativity with quantum mechanics, must take over. In that theory, the infinities might dissolve into something finite and describable. Until then, singularities remain puzzles at the edge of physics. They are places where our understanding stops and our models break. What lies beyond them is hidden, waiting for a deeper theory of reality. Whether information vanishes inside a black hole is an open question. When matter falls into a black hole, it seems to disappear forever. But in physics, information, the details about the state of a system is supposed to be preserved. So what happens to the information locked inside a black hole? Stephen Hawking showed that black holes can slowly evaporate through radiation. But if they vanish completely, where does the information go? If it is destroyed, the laws of quantum mechanics would be violated. If it escapes, then somehow the information must leak out through the Hawking radiation, a process no one fully understands. This puzzle, known as the black hole information paradox, has challenged physicists for decades. Some think the information is stored on the event horizon itself. Others argue that black holes might connect to other regions of space-time, allowing the information to escape. Still others think our very understanding of quantum mechanics may need revision. The fate of information in a black hole is one of the most important open questions in physics. It touches not only on black holes, but on the deepest foundations of reality. Hawking radiation is predicted, but no one has ever seen it. In the 1970s, Stephen Hawking made a stunning prediction. Black holes are not truly black. Quantum effects near the event horizon should cause them to emit faint radiation, slowly losing mass over unimaginable timescales. Eventually, they could evaporate entirely. This radiation, now called Hawking radiation, is one of the most famous predictions in modern physics. Yet, we have never observed it. Real black holes are surrounded by hot gas and violent environments that overwhelm the faint trickle of radiation. Detecting it directly may be impossible with current technology. Still, the idea has huge consequences. It ties together quantum theory, relativity, and thermodynamics. It suggests that black holes have a temperature, and that space-time itself is more dynamic than we realized. Laboratory experiments have tried to create analogues of Hawking radiation using sound waves and fluids, but these remain indirect hints. Whether Hawking radiation truly exists remains unproven. If it does, it will reshape our understanding of black holes. If it does not, something even stranger must be happening at the edge of spated black holes. May even be doorways to other worlds we do not yet know. Black holes push physics to its limits. Inside them, space and time bend in ways we cannot fully describe. Some solutions to Einstein's equations suggest that black holes could connect to other regions of space-time. Tunnels, known as wormholes. In theory, entering a black hole might lead elsewhere, but this remains speculation. Wormholes, if they exist, may be unstable. The intense gravity of a black hole might destroy anything that tries to pass through, and yet, the mathematics leaves the possibility open. Some physicists suggest that the singularity at a black hole center could mark a bridge to a new universe with its own space and time. Others think black holes might recycle information, seeding the birth of new cosmic regions. For now, we cannot test these ideas. No signal can escape a black hole's interior, and so its secrets remain hidden. Still, the idea that black holes may be more than cosmic graves, that they could be gateways to something beyond, is one of the most tantalizing mysteries of all. Asterisk. We still cannot explain how the very first stars were born. When the universe was new, it was a dark, simple place. There were no galaxies, no planets, no metals or complex chemistry. Only clouds of hydrogen and helium drifted in the expanding cosmos. At some point, those clouds collapsed to form the first stars, ending the cosmic dark ages and lighting the universe for the very first time. But exactly how this happened remains a mystery. These first stars, called population 3 stars, would have been enormous, hundreds of times the mass of our Sun, burning hot and bright, but living only for a few million years before exploding as powerful supernova. They seeded the cosmos with the first heavier elements, paving the way for later generations of stars and eventually for life. The problem is that we have never seen one. No population 3 star has been observed. They lived and died so quickly, so long ago, that direct evidence is missing. Astronomers look for indirect clues in the chemical fingerprints of ancient stars, hoping to find hints of their violent births. The James Webb Space Telescope may finally glimpse their light. But for now, the exact process that sparked the first stars remains one of the great open questions in astronomy. Some galaxies formed, supermassive black holes far too quickly. At the heart of nearly every galaxy lies a supermassive black hole, millions or billions of times more massive than our Sun. We know how black holes can grow by swallowing gas, stars, and even other black holes. But in the early universe, we see black holes that grew far too large, far too fast. Some of these giants already existed less than 1 billion years after the Big Bang, according to our models. There simply was not enough time for them to grow so big through ordinary processes. This leaves us with a puzzle. Did they form from the collapse of enormous primordial clouds, skipping the small steps entirely? Did they grow from the deaths of massive first-generation stars that collapsed into black holes much larger than we expect? Or is there a mechanism we have not discovered yet, allowing them to feed and expand at astonishing rates? These ancient black holes challenge our understanding of galaxy evolution. If we can solve their mystery, we may unlock the story of how galaxies themselves came to be. For now, they remain cosmic enigmas, giants that should not exist so soon after the universe began. No one knows why so many galaxies take on spiral shapes. When we imagine galaxies, we often picture elegant spirals, sweeping arms of stars curling outward like cosmic pinwheels. The Milky Way is one of them. But why should galaxies form such intricate spiral patterns? The answer is not clear. One idea is that spiral arms are density waves, like traffic jams on a highway. Stars move through them, bunching up as they pass, creating the illusion of permanent arms. Another theory suggests that spirals may be shaped by interactions. Galaxies tugging on each other with gravity, stirring stars into curving arms. Simulations can recreate spiral structures, but not with perfect consistency. Spirals are not rare. In fact, they are common. And yet, their exact origin and stability remain unsettled. Why some galaxies form beautiful spirals while others become elliptical blobs is still an open question in astrophysics. When we look at the night sky and see the Milky Way stretched across it, we are looking from inside one of these mysteries. Our home galaxy's graceful arms are both familiar and unexplained. Fast radio bursts flash across the cosmos, and their cause remains a mystery. In 2007, astronomers detected a powerful radio signal lasting only a few milliseconds. Since then, hundreds more have been found scattered across the sky. These signals are called fast radio bursts, or FRBs. Each one releases as much energy as the sun does in a year, but in the blink of an eye, what causes them? Some FRBs repeat, suggesting they come from ongoing processes like magnetars, highly magnetic neutron stars that can flare with incredible energy. Others appear only once, hinting at catastrophic events such as the collapse of a star or the merger of compact objects, but no explanation fits them all. FRBs travel across billions of light years, distorted and stretched by the matter between galaxies. They may even help us map the distribution of matter across the universe. But until we know their source, they remain cosmic puzzles. Every so often, the universe sends us a brief, powerful shout across the void. We can hear it. We can measure it. But we still do not know who or what is speaking. Pulsars shine with perfect regularity that their precision still puzzles us. Pulsars are the collapsed remnants of massive stars, neutron stars that spin rapidly, sweeping beams of radiation across space like cosmic lighthouses. Discovered in 1967, they were so regular at first that scientists wondered if they might be signals from intelligent life. Today, we know they are natural, but their precision remains astonishing. Some pulsars keep time better than our best atomic clocks, rotating hundreds of times per second without missing a beat. How can an object so extreme, a star crushed into the size of a city, maintain such stability? The answer lies in their incredible density and strong magnetic fields, but the details are not fully understood. Pulsars can also glitch, suddenly changing their rotation speed in ways we cannot yet predict. These glitches may come from interactions deep within their superfluid cores, where physics is unlike anything on Earth. Pulsars are laboratories of extreme physics, but they still keep secrets. Their rhythms remain some of the most mysterious and precise signals in the universe. Magnetars erupt with strange bursts of energy we do not fully understand. A magnetar is a kind of neutron star with a magnetic field 1,000 times stronger than a normal neutron star, and 1,000,000,000,000 times stronger than Earth's. These magnetic fields twist and snap, releasing sudden, violent bursts of radiation. Magnetars can unleash more energy in a single second than the sun produces in 100,000 years. We detect them as intense X-ray and gamma-ray flares. But what exactly triggers these eruptions remains uncertain. Are the bursts caused by starquakes, shifts in the crust of the neutron star under magnetic stress? Or are they caused by sudden reconfigurations of the magnetic field itself, releasing energy like a snapping cosmic rubber band? Some fast radio bursts have even been linked to magnetars, suggesting they might explain at least some of those mysterious signals. But the full picture is still missing. Magnetars are rare, with only a few dozen known, but their power is staggering. They are reminders that the universe contains engines of energy we still struggle to comprehend. Cosmic rays strike Earth with incredible power, and we do not know where they come from. Every second, high-energy particles, called cosmic rays, rain down on Earth from space. Most are protons traveling near the speed of light. Many come from the sun or from supernova. But some are so energetic, so powerful, that we have no idea where they originate. The most extreme cosmic rays carry the energy of a fast-pitched baseball packed into a single particle. No known process should be able to accelerate them to such speeds. They may come from supermassive black holes, from active galaxies, or from exotic processes we do not yet understand. These particles crash into Earth's atmosphere, creating showers of secondary particles that we can detect on the ground. Observatories like the Pier Orga Observatory in Argentina track them, trying to trace their paths back to their origins. But magnetic fields in space bend their trajectories, erasing the clues. Cosmic rays are constant visitors, yet their most powerful examples remain unexplained. They remind us that somewhere in the universe, nature runs particle accelerators far beyond anything humans can build. Asterisk. Vast cosmic voids stretch across space, and their origins remain unclear. The universe is not evenly filled with matter. Instead, galaxies form a vast cosmic web, clusters and filaments separated by enormous voids. Some of these voids span hundreds of millions of light years, nearly empty of galaxies. Why are they there? Simulations suggest that gravity pulls matter into filaments, naturally leaving empty spaces behind. But the largest voids are bigger than expected, raising questions about how they formed. Do they hint at new physics, perhaps in the way dark energy shapes structure? Or are they just statistical extremes, rare but possible? Voids affect how light travels across the universe. They may even offer clues about the nature of dark energy itself. But for now, their true origins remain uncertain. Looking into a cosmic void is like staring into nothingness on the largest possible scale. They are among the loneliest regions in existence. Vast expanses with no clear explanation. How the universe will end is still an unanswered question. The universe had a beginning, but will it also have an end? Scientists consider several possibilities, each dependent on the nature of dark energy and the balance of cosmic forces. In one scenario, the universe expands forever, cooling until stars burn out and galaxies fade, leaving only cold darkness. This is the heat death. In another, the expansion may eventually reverse, pulling everything back together in a big crunch. A third possibility is the Big Rip, where dark energy grows stronger over time, tearing apart galaxies, stars, planets, and eventually even atoms. Which will it be? We do not yet know. Observations suggest expansion will continue, but the details of dark energy remain too uncertain to decide. The universe may last for trillions of years, or it may meet a more dramatic fate. For now, the ultimate future of everything, of stars, galaxies, and life itself, remains one of the greatest unanswered questions of science. Something triggered cosmic inflation, but no one knows what. In the earliest fraction of a second after the Big Bang, the universe is thought to have expanded faster than the speed of light in a process called inflation. This theory explains why the cosmos appears so smooth and uniform, and why tiny fluctuations seeded the galaxies we see today. But what caused inflation? That remains a mystery. Some theories propose a field of energy, the inflaton that briefly dominated the universe before fading away. Others suggest inflation is tied to the quantum structure of space-time itself. We see its fingerprints in the cosmic microwave background, where patterns match what inflation predicts. But the true cause, and whether inflation really happened as described, is still debated. Something made the universe grow unimaginably fast, creating the stage for everything that followed. But the spark that drove this inflation is still unknown. A hidden chapter in the story of creation, the origin of life on Earth, is still unknown. Life on Earth began more than 3.5 billion years ago, but the details of its origin remain hidden. Fossil evidence shows that microorganisms were already thriving not long after the planet cooled. But how did non-living chemistry cross the threshold into life? One idea is that life began with simple molecules, self-organizing into chains capable of storing information. Perhaps RNA before DNA. Another is that life emerged from the energy-rich environment of hydrothermal vents on the ocean floor, where hot water, minerals, and chemistry combined. Still others propose that life's building blocks may have arrived from space, carried on comets or meteorites that bombarded the young Earth. Each idea has support, but none are proven. Scientists have managed to create amino acids and other basic molecules in laboratory conditions, thought to mimic the early Earth, but producing a fully living system remains beyond reach. The origin of life may have been a unique event, or it may be a natural outcome whenever the right conditions exist, until we uncover clearer evidence. The moment when chemistry first awakened into biology remains one of science's deepest mysteries. We do not know if life began in the ocean or on land. Our planet offered many possible cradles for the first life. The ocean, covering much of Earth, seems like the obvious candidate. Hydrothermal vents, where hot water and minerals pour from the seafloor, provide rich chemistry and constant energy. Many scientists believe life may have begun there with molecules assembling inside natural mineral compartments. But there is another possibility. Some researchers argue that shallow pools on land, subject to cycles of drying and refilling, could have concentrated molecules and driven the reactions needed to form life's building blocks. Ultraviolet light from the sun, often destructive, could also have powered key steps in these reactions. Both environments seem plausible. Each offers strengths, and each faces challenges. The ocean dilutes molecules, making it harder for them to interact, while land-based pools may have been too unstable. Until stronger evidence emerges, we do not know whether life first stirred in the deep oceans or in the shallow waters of land. The answer remains hidden in the deep past. In rocks and fossils that have long since transformed, no one knows how the first living cells were formed. Life is defined not just by chemistry, but by organization. Modern cells are intricate structures with membranes that separate them from the outside world, and with molecular machines carrying out countless reactions. But how did the first cell arise from lifeless chemistry? One possibility is that fatty molecules naturally present on the early Earth formed bubbles that trapped useful chemistry inside. These primitive membranes could have allowed energy and molecules to flow while protecting fragile chains of RNA or proteins. Over time, the chemistry inside could have become more complex, eventually becoming self-sustaining. Experiments show that simple membranes can indeed form spontaneously in the right conditions. But how the leap from these primitive compartments to the complexity of a living cell occurred is still unknown. This transition from disorderly chemistry to the first organized cell remains one of the great mysteries of biology. Until we understand it, we cannot say how life truly began. DNA chose a very specific shape, but why it did remains a mystery. All life on Earth uses the same molecule to store information, DNA. Its double helix is elegant and universal, carrying the instructions for every organism. But why this molecule, and why this shape? Chemistry allows for many possible ways to store information. RNA, for instance, is simpler and may have come first, but somewhere in life's early history, DNA took over as the master code. Its stability, its ability to replicate reliably, and its capacity to carry immense amounts of information made it uniquely suited. Yet we do not know why DNA's specific structure, a double helix with precisely paired bases, became the solution that all life depends on. Was it inevitable, dictated by chemistry? Or was it an accident, a single successful outcome among many failed alternatives? The universality of DNA suggests it may be the best answer nature could find. Still, why life chose this exact path remains an open question, hinting at deep mysteries in the chemistry that underpins existence. Asterisk. The origins of viruses are still unclear. Viruses are strange entities. They are not alive in the traditional sense. They cannot reproduce on their own, relying instead on hijacking the machinery of living cells. Yet they are not merely inert molecules. They evolve, adapt, and influence the course of life on Earth. Where did they come from? Some scientists think viruses are relics of the RNA world, survivors from before fully living cells evolved. Others believe they began as pieces of genetic material that escaped from cells and learned to copy themselves. A third possibility is that they were once living organisms that became stripped down to their simplest form. The truth may be that viruses arose in more than one way, their origins as diverse as life itself. What is clear is that they are ancient. They may even have played a crucial role in the evolution of complex life, transferring genes between organisms. Viruses blur the line between life and non-life, and their beginnings remain one of biology's most enduring mysteries. Some molecules became alive, while countless others did not. We do not know why. The early Earth was a chemical playground. Simple molecules formed everywhere, from deep-sea vents to volcanic pools to lightning-struck atmospheres. Among them, Some began to link into more complex chains like amino acids and nucleotides. But only a tiny fraction of this chemistry crossed the line into life. Why those molecules and not others? What special property allowed some to organize into self-replicating systems? Was life inevitable once the right ingredients came together? Or was it a rare accident dependent on chance events? Experiments suggest many building blocks of life can form under natural conditions, but creating a self-sustaining, evolving system remains elusive. The leap from chemistry to biology is vast, and we do not yet know how it happened. This uncertainty raises profound questions. If life is inevitable, then the universe may be filled with living worlds. If it was a fluke, then we may be utterly alone. The mystery of why some molecules became alive while others remained inert is one of the most important unanswered questions in science. We still do not know if life exists anywhere else in the universe. Earth is the only place we know where life exists. But with billions of stars in our galaxy and billions of galaxies beyond, it seems unlikely that we are alone. Still, despite decades of searching, no clear evidence of extraterrestrial life has been found. We have discovered thousands of exoplanets, many in the habitable zone where liquid water could exist. We know that organic molecules are common in space, found on comets, in clouds, and on distant moons. Mars shows signs of a wetter past. Europa and Enceladus hide oceans beneath their icy crusts. Conditions for life seem abundant, and yet the silence persists. We have not detected signals, nor found microbes on Mars, nor uncovered alien fossils. It is possible life is common, but hard to detect. Or it may be exceedingly rare, requiring conditions we do not yet understand. Until we find even the simplest alien microbe, the question of whether life exists elsewhere remains unanswered. Could life form from a chemistry completely different from ours? We do not know. All life on Earth is built on the same foundation: carbon, water, DNA, and proteins. But must it be so? Could life exist with a different chemistry entirely? Some scientists think silicon, abundant and capable of forming long chains, could serve as the backbone of alien life. Others imagine organisms that use ammonia instead of water, or exotic biochemistries thriving in methane seas like those on Saturn's moon Titan. Still others wonder if plasma, magnetic fields, or information itself could host something like life. We do not yet know the answer. All of our definitions of life are shaped by a single example: Earth. It may be that carbon and water are the only real solution. Or it may be that the universe holds living systems stranger than we can imagine. If we discover alien life, it may look nothing like us. It could challenge our very definition of what it means to be alive. How common truly habitable worlds are is still uncertain. Astronomers have discovered thousands of planets orbiting other stars. Many are small and rocky, some in the habitable zone where liquid water might exist. But how many are truly habitable? That is still unknown. Habitability depends on more than distance from a star. Planets need the right atmosphere, magnetic protection, and long-term stability. Some may be scorched by radiation, others frozen by lack of heat. Moons may be habitable too, with oceans beneath their icy crusts, but we cannot yet measure them directly. The galaxy may be rich in habitable worlds, or they may be rare jewels. Right now, we cannot say. Each discovery brings us closer, but the true frequency of Earth-like conditions remains one of the great, open questions in astronomy. we still cannot answer the oldest question of all. Are we alone? For as long as humans have looked at the stars, we have wondered whether life exists beyond Earth. Despite the size of the universe, despite the abundance of planets and the chemistry of life scattered across space, we still have no answer. We listen for signals with radio telescopes. We send probes to planets and moons. We analyze the atmospheres of distant worlds for signs of life. But so far, the silence is complete. It may be that life is common, but intelligent civilizations are rare or short. It may be that life is rare at every level, and we are a singular accident. Or it may be that life is everywhere but hidden from us by distance or difference. The question remains open. Are we a lonely spark in a vast empty universe? Or one voice in a cosmic chorus we have not yet heard? Until we find evidence, the answer to this oldest of questions remains unknown. Consciousness arises from the brain, but we do not know how. Every thought you have, every memory, every flicker of awareness seems to arise from the brain. Scientists can measure electrical signals moving across neurons. They can switch awareness off with anesthesia. And they can even track the brain's activity when you focus on a picture or a sound. Yet none of this explains why there is an inner experience at all. Why should firing neurons create the feeling of being alive? A brain scan can show activity in the visual cortex when you see a sunset, but it does not explain why that experience comes with the glow of red and gold inside your mind. It shows circuits for sound, but it does not explain why hearing your favorite song feels so moving. Researchers have ideas that consciousness appears when information spreads across the brain, or when neurons form certain patterns, or even that awareness is a deeper property of the universe itself. But none of these ideas truly explain the leap from matter to mind. Consciousness is the most ordinary thing. It is what you are experiencing right now. And yet when we try to explain it, it slips through our fingers. We know it arises from the brain, but the how remains the deepest mystery of all. Asterisk. Dreams fill our nights, but their purpose is still unknown. Every night, as you sleep, your mind conjures worlds. Some are vivid, filled with people and places you know. Others are strange and fragmented, dissolving as soon as you wake. These are dreams, and though we all experience them, no one truly knows why they happen. Some scientists think dreams are the brain's way of practicing. They may replay memories, strengthening useful connections. Others believe dreams help regulate emotion, allowing you to work through fear, sadness, or conflict in a safe, unreal space. Some say they are simply random firings of a sleeping brain, patched together into stories. What makes dreams more puzzling is that they can be so powerful. A nightmare can wake you in terror even though you are safe in bed. A good dream can leave you smiling all day. Sometimes dreams even solve problems. Writers, artists, and scientists have all described breakthroughs that came to them in sleep. We know the brain is active while we dream, especially during REM sleep, when the eyes flicker beneath closed lids. But the purpose behind it remains elusive. Dreams are familiar nightly journeys into strange lands, yet their true meaning is still hidden. Time feels slower or faster depending on us, and no one knows why. Think of a moment when time seemed to slow to a crawl, a near accident, a sudden fright, an intense experience. Now think of the opposite. A holiday that seemed to vanish in an instant, or hours that disappeared when you were fully absorbed in something you loved. Clock time is steady, But our sense of time is anything but. Why? No one knows for sure. Some believe the brain has an internal clock, and that emotions like fear speed it up, while calm states slow it down. Others suggest our brain judges time by the number of events it processes. A moment filled with new details feels longer, while a routine one feels shorter. This could explain why childhood summers seemed endless, while adult years slip past more quickly. Novelty stretches our perception, and routine compresses it. But it is only a theory. What we do know is that time in the mind is elastic. It stretches, contracts, and sometimes even seems to stand still. The seconds and minutes are constant, but our experience of them is mysterious, flowing according to rules we do not yet understand. We do not yet understand how memories are stored and recalled. Your entire life, your first day of school, your happiest moments, your deepest regrets, is stored somewhere inside your brain. And yet, how those memories are kept and how they return when you need them is still a mystery. Scientists know that memories are not like files in a cabinet. They are patterns of activity across many neurons spread across different regions. The hippocampus helps weave these patterns, acting as a kind of index. But exactly how the brain encodes a memory and later pulls it back is not fully understood. Sometimes memories change when we recall them, being reshaped before they are stored again. Sometimes we even create false memories that feel completely real. Why do some memories last a lifetime, while others fade in days? Why does a certain smell suddenly unlock a vivid scene from childhood? Experiments show glimpses, neurons that fire when a specific face is seen, brain activity that mirrors memory recall. But the full picture is missing. Memory is the glue that makes us who we are, and yet the machinery behind it, how moments become part of us, and how they return years later, is still unknown. Our emotions run deep, but their origins remain mysterious. Emotions shape every part of life. Joy pushes us forward. Fear holds us back. Anger flares. Sadness weighs heavy. But where do they come from? Scientists know that emotions involve the body as well as the brain. Your heart races when you are afraid. Your stomach knots when you are anxious. Tears well up when you are sad. But the origins of these feelings are still debated. Are emotions hardwired, ancient survival tools built into our biology? Or are they constructed by the brain, shaped by culture, memory, and interpretation? We know certain brain regions play a role: the amygdala for fear, the insula for disgust, the prefrontal cortex for regulation, but no single emotion center exists. Music can bring goosebumps. Scents can trigger sudden nostalgia. Sometimes we do not even know why we feel the way we do. Emotions are powerful guides, steering our choices often more than reason does. Yet the way they arise, the way they take hold of the body and the mind, remains one of the most intimate mysteries of being human. Creativity appears in sudden sparks, but we do not know where it comes from. An artist stares at a blank canvas, a writer at an empty page, a scientist at an unsolved problem. Hours may pass with nothing, and then suddenly an idea arrives, clear, surprising, alive. Where did it come from? Creativity feels like a spark, but its origin is hidden. Some say it is the brain mixing and matching old ideas in new ways. Others think it requires stepping away, letting the subconscious work while the conscious mind rests. Many breakthroughs in history have come not at desks, but in dreams, showers, or quiet walks. brain scans suggest different networks are involved, some generating ideas, others judging them. But this still does not explain the moment of inspiration. Why does the solution arrive suddenly with such force? Why do some people overflow with creative ideas while others struggle? Creativity is one of humanity's greatest gifts, shaping art, science, and progress. Yet the place where ideas come from, that quiet leap from nothing to something, is a mystery we still cannot explain. Déjà vu makes the present feel repeated, and no one knows why. You step into a room you have never been in before, and suddenly everything feels strangely familiar. You know what will happen next, though you do not. This is déjà vu, and it remains one of the strangest mysteries of the mind. Scientists suggest it may be a trick of memory. Perhaps the brain misfires, creating a false signal of familiarity without a real memory behind it. Others think it happens when one part of the brain processes an experience slightly before another, making the moment feel like a repeat. Still others suggest it comes from similarities between a current scene and a forgotten past one, fooling the mind. What makes déjà vu so mysterious is the intensity. For a few seconds, reality feels doubled, both new and remembered. Almost everyone experiences it, yet no one can predict when or why. Déjà vu reminds us that memory and perception are fragile, and that the brain sometimes tricks us in ways we do not yet understand. Placebos can heal, but the power behind them is still a mystery. Imagine taking a pill, being told it will ease your pain, and then actually feeling better even though the pill contained nothing at all. This is the placebo effect, and it is real. Doctors have seen placebos reduce pain, ease depression, and even calm symptoms of Parkinson's disease. The effect is thought to come from expectation. The belief that something will help triggers real changes in the brain and body. Placebos can release natural painkillers, alter brain chemistry, and affect the immune system. What makes the placebo so strange is that it can work even when people know they are taking one. Somehow, the ritual of treatment, the pill, the doctor, the belief, taps into hidden healing pathways. But why some people respond strongly to placebos and others do not, is still unknown. The placebo effect blurs the line between mind and body, showing us that belief itself can sometimes heal in ways we still do not fully understand. Asterisk. Consciousness may not be limited to humans, but we do not know how far it extends. Animals show signs of awareness. Dolphins recognize themselves in mirrors. Elephants mourn their dead. Crows solve puzzles and remember human faces. Dogs clearly feel joy, fear, and loyalty. Even octopuses, with their alien nervous systems, show curiosity and playfulness. But are these true forms of consciousness? Or are they simply instinct and learned behavior? Scientists debate how far awareness spreads through the animal kingdom. Some argue that any creature with a nervous system may have some spark of experience. Others suggest that consciousness may exist on a spectrum, with humans at one extreme but many other creatures somewhere along the line. Plants even communicate, react, and adapt in surprising ways. Do they have some primitive form of awareness, or is that only metaphor? We cannot yet say. Consciousness may be more widespread than we know, or it may be unique to us. Where the boundary lies remains an open question. We do not know why humans sleep at all. We spend a third of our lives asleep. It is as essential as food or water. Without sleep, we weaken, hallucinate, and eventually die. And yet, no one fully understands why sleep exists. One idea is that sleep restores the body, allowing cells to repair themselves and the immune system to strengthen. Another is that it clears toxins from the brain, a kind of nightly cleansing cycle. Some suggest sleep is essential for memory, organizing the day's experiences and weaving them into long-term storage. But none of these explanations fully capture why evolution would keep such a vulnerable state. While asleep, we are defenseless, unable to run or fight. Why would nature favor such a risk unless the benefits were profound? Whatever its purpose, sleep remains one of biology's great mysteries. Hiding behind closed eyes every night, aging slowly breaks the body, but no one knows exactly why. From the moment of birth, living things begin to age. Cells divide, DNA mutates, proteins falter, and slowly, systems fail. We call it aging. But why must it happen? Some scientists suggest aging is simply damage accumulating over time, the unavoidable wear and tear of existence. Others propose it is programmed into our biology, an evolved strategy to clear the way for new generations. Experiments show that aging can be slowed in animals by altering genes, by caloric restriction, or by resetting cellular clocks. Some organisms seem to escape aging almost entirely, like certain jellyfish that can revert to earlier stages of life, but humans cannot. Despite medicine extending our lifespans, the root cause of aging remains unknown. Why bodies grow old and fail is a question science has not yet solved. We do not know why we die. Death is universal. Every living thing eventually comes to an end. We know how it happens. Organs fail, cells stop dividing, the brain shuts down. But why must it happen at all? Could life exist without death? Some biologists argue that death is simply the cost of complexity. Systems wear out and cannot maintain themselves forever. Others believe that death is an evolutionary necessity, clearing space for younger generations to adapt and survive. But these are ideas, not answers. Even if we slow aging or repair the body, death may remain unavoidable. It is one of the deepest mysteries, not just how life begins, but why it must end. We do not know why we dream of life after death. Across every culture and every age, humans have imagined that something of us survives beyond death. Some see a soul, others a spirit, still others a continuation in another form. Religion, philosophy, and myth all offer possibilities, but science cannot say. Near-death experiences, visions of light or loved ones, feelings of floating outside the body, these are reported around the world. Are they glimpses of something beyond, or are they the brain's final illusions as oxygen runs low? No experiment can settle this. The question of what, if anything, lies beyond death remains outside the reach of science. But the universality of the idea suggests it is woven into us. Whether as comfort, fear, or mystery, the thought of life after death is as old as humanity itself. The future of intelligence is uncertain. Human intelligence created art, science, and technology. Now we are building machines that can think in ways we once believed were uniquely ours. Artificial intelligence writes, paints, and solves problems. Some wonder if AI could one day surpass us, creating a new kind of mind. But what is intelligence? We cannot even define it precisely. Is it problem-solving? Creativity? Animals show forms of intelligence. Machines may too. But whether they will ever experience, feel, or dream, we do not know. The boundary between human thought and artificial thought is still being explored. The future of intelligence, whether it stays with us, spreads to our machines, or takes forms we cannot imagine, remains an open question. Free will feels real, but we cannot prove it exists. Every day you make choices. What to eat, where to go, what to say. It feels as if you are the author of those decisions. But are you? Neuroscience shows that brain activity often begins before a person is consciously aware of a choice. Some experiments suggest the decision is made in the brain before the mind experiences it. Does this mean free will is an illusion? Or does it mean our understanding of decision-making is incomplete? Perhaps consciousness and unconscious brain activity are more entwined than we know. Philosophers argue endlessly over the question: if free will does not exist, what does that mean for morality, responsibility, and meaning? If it does exist, how does it arise from physical matter? For now, the truth remains uncertain. Free will feels like the most intimate reality, yet it may be one of the greatest mysteries of all. The universe may be stranger than we can imagine. With every mystery comes the reminder that our understanding is small. For all the discoveries we have made, black holes, DNA, evolution, quantum mechanics, we are still surrounded by questions. Some may never be answered. Some may unravel in ways we cannot yet conceive. But in the silence of the night sky, in the flicker of stars across the dark, the mysteries remain. Why there is something instead of nothing. Why time flows forward. What dark matter and dark energy truly are. How life began. Why we are conscious. Whether we are alone. The questions stretch endlessly, like the universe itself. They invite us not just to seek answers, but to wonder, to accept that mystery itself is part of existence. And in that unknowing, there is beauty, there is humility, and there is peace. So, as you drift to sleep, let these questions carry you. The universe is vast, strange, and filled with secrets. And though we may never know them all, perhaps that is not a failing, but a gift. For mystery is the dream of the cosmos, and we are part of that dream. Good night, and may the mysteries of the universe watch over your rest. Asterisk.